안녕하십니까. 네덜란드 응용과학 연구기구인 TNO와 진행한 POC 결과에 대해서 발표할 EGIS 기술연구소 이주용입니다. 오늘 보여드릴 것은 단순한 데이터의 3차원 시각화가 아닙니다. 파편화된 데이터가 어떻게 의사결정 구조로 전환되는가에 대한 이야기입니다. 위기 상황에서도 언제나 데이터는 존재합니다. 문제는 그것이 대응을 위한 실행 단계로 연결되지 않는다는 점입니다. 파편화된 데이터만으로 즉각적인 대응은 불가능합니다. 이번 TNO와 진행한 POC의 목적은 일상과 위기 상황을 동일한 구조에서 비교 가능하게 만드는 것, 그리고 예측을 실행으로 전환하는 것입니다. 우리는 근본 POC를 통해 예측하고 인지하여 실행으로 이어지는 의사결정의 파이프라인을 만들고자 했습니다. 근본 POC는 단순한 기술 검증이 아닌 구조적인 검증입니다. 근본 POC의 타겟 날짜는 2022년 2월 18일 금요일이었습니다. 이날은 네덜란드를 포함한 유럽 일대 큰 피해를 일으킨 폭풍 유니스가 강타한 날입니다. 내륙 최고 풍속이 시속 145km를 기록하였고 네덜란드 왕립기상청이 최고 경보 단계인 코드 레드를 발령하는 듯 강력한 것이었습니다. 이러한 복합 재난 상황에서 네트워크 단위 리스크를 즉시 인지할 수 있는가? 이것이 이번 POC의 출발점입니다. 이번 POC를 함께 수행한 네덜란드의 TNO는 과학을 실행 가능한 모델로 만드는 기관입니다. EGIS는 그 모델을 실행 가능한 플랫폼으로 확장하였습니다. 이번 프로젝트는 과학적 모델과 실행 플랫폼의 결합을 통해 의사결정 지원 구조의 토대를 만드는 것이었습니다. 근본 POC를 함께 수행한 TNO 측 연구 책임자는 타우픽 바크리 박사님입니다. 그는 위험을 정량화하였고 위험 신호를 검증하며 운영 로직으로 연결하는 등 다양한 연구를 수행해 왔습니다. 바쁘신 와중에 멀리 네덜란드에서 직접 EGIS 컨퍼런스를 위해 방문해 주신 타우픽 바크리 박사님께 환영의 박수를 부탁드립니다. Please give a warm welcome to Dr. Taoufik Bakri. 이제 TNO의 POC 진행 내용에 관한 설명을 먼저 들어보겠습니다. 연구 책임자이신 타우픽 바크리 박사님을 한 번 더 박수로 모시겠습니다.
Thank you very much for having me. Sorry, my Korean is not good, so I will speak English. I'll try to speak slowly so everybody can follow. I'm going to talk a little bit. My talk will be a bit boring, I'm sorry, but it is a bit technical. I'm going to talk about what we did together with EGIS and how the work we did together can support policymakers in making decisions for their cities. So my talk will be, I'll try to do it in 20 minutes. I will explain a bit the challenges policymakers are facing in the Netherlands, but in South Korea they are the same, the challenges are the same. They are not really different from what the policymakers are facing in the Netherlands. I will be a bit brief because Jay already introduced TNO. Then we'll start digging into the content of the work we did. I'll try to explain a bit the technical stuff, what you can do with data, the data you collect from the country, from the highways, and combine it with weather data and see what kind of useful information you can extract to implement in digital twins. So, the challenges we are facing and the policymakers are facing worldwide are varies. You can see urbanization, the aging population. You have that in the South Korea. We have that in the Netherlands as well. Scarcity of space. You have that in South Korea. Where do you build housing? Where do you put housing and neighborhoods? Where do you put schools, hospitals, universities? We don't have a lot of space in the Netherlands. So these are all really challenges that policymakers are facing. And they have to make decisions, and it is becoming more and more complex because all these domains are interconnected. You cannot just say, I will take population aging, I will take electrification. They have impact of each other. So it becomes more and more complex. And the city, in a way, it's just a living organism. Everything is connected. So you can just take one thing. I am an expert in traffic. I will take only traffic. Well, traffic is affected also by other stuff, by infrastructure, by policy decisions and other things. For the talk now, we will focus on what we did on the use case together with EGIS. And we just tried to look what kind of useful information we can extract from data collected from weather and traffic. Here again, the policymaker is really in a serious situation because there is a lot of disruptions coming at the policymaker. Climate change, a lot of different things, electrification, the geopolitical situation. So how do you deal with all these things at the same time and making sound decisions? And the time to decision is really under pressure. So you have to decide quickly, and you want to really measure whether your policy, your decisions had the good and desired effect on what you wanted to achieve. So you can design a policy, but you want to measure, was it a good decision or was it a bad decision? So this is the domain we're going to focus on right now, and this is a highway in the Netherlands. So it's really not quite different from Korea. You have lanes, you have bad weather. In the Netherlands we have a lot of rain, and this rain is getting more frequent and heavier, more heavy. We see really a change in the rainfall in the last 10 years. It is more frequent and heavier, and also in the summer. So we need some smart ways to extract information and make the policymaker more proactive and not reactive. Well, what are then the challenges? If we just reduce all the problems now to just traffic, what are the challenges? Well, there is an unexpected congestion. Why is there congestion there at 10 o'clock? Or why is here a problem? So we need to understand where these disturbances in traffic come from. What is the impact of weather? When you have weather, can we understand, okay, if there is heavy rain on the country, where on the network we will have a problem? And how much time we will have when the rain starts falling before the lanes, we will start closing lanes because the highway is closed because of the water. So plannings and roadworks in the Netherlands, we have a huge problem coming at us, at the policymaker. Most of the bridges and highways were constructed after the Second World War, so it's in 1945. And they are now really very old and need to be renovated. So how do you organize this renovation? So how do you do it? You need really to understand what the impact is on traffic, what the impact is on the cities, on the logistic domain, so people should have access to cities to deliver goods and stuff. So it is a very, very complex problem to deal with. So in a sense, we just want to understand when traffic starts to deteriorate. Do we really understand why? What is the reason for that? Okay, this is, I will skip this, just one thing. This is, who are we? So why I am here and who are we? We are TNO. Jay told a lot about TNO, so I will skip it. I'll just tell we are active in those 6 domains. So we are really diverse and work on. I am from the mobility, built and environment, so I originate from that. But we have contacts with the defense. There is a unit doing defense for the military and the top secret stuff for the Netherlands military. There is the energy department, and there is a healthy living that look at how people can be healthy and live longer and that kind of things. The high-tech industry is also very important unit we work with that work on quantum computing, which is very important when you have to do much heavy calculations. So we have 6 units and a lot of expertise present that we can just call. If you need a physicist, there is a physicist somewhere at TNO, and you call it, and then you have your joint work. Who I am? I am Taoufik Bakri. You see me maybe with less hair than in the picture there. My expertise is I am a mathematician. I did my PhD in mathematics, and I work at TNO for about 20 years. My domains of expertise are nonlinear dynamics, bifurcation chaos theory, travel time predictions that I did a long time with TNO, big data, machine learning, federated learning. I collaborated in projects with big companies like Google, Cisco, and Inrix, mainly focused on traffic. And I like working interdisciplinary because the problems we are facing, you just not need a traffic engineer or just a mathematician, but you need different disciplines together to solve really the problem. My role now at TNO is I'm responsible for the data and artificial intelligence strategy. So in that role, I work and I come here also into Korea to see how can we collaborate in joint projects like this one. Okay, so let's dig into the problem. What we did, what kind of data we used, what is available in the Netherlands, so we can compare maybe with the situation in Korea. So the data we have in the Netherlands is quite rich. What you look here is the map of the Netherlands traffic network, and we have induction loop detectors at the lane level. So each lane we have induction loop detectors that measure the number of cars per minute and their average speed. So we know exactly at each location how many cars each minute have passed and what was their average speed. So those sensors are collecting data every minute. The Ministry of Transportation is collecting this data in a server and then pushing it to universities and research institutes like TNO, and I am using this data to generate information. So there are many types. So this data contains also whether there are lane closed and what kind of speed limit is projected on the side. Besides that, we have also these were locations where you can measure, but we have also monitoring travel time on a trajectory. So we have from A to B, we monitor how much travel time is needed to go from A to B. This data is usually collected in urban areas to see how accessible the city is. So this data we have every minute, and we have an archive of more than 10 years, so from 2004 until now. We have real time, we collect this data real time. So you have this data, and then what do you do with it? Because it's a lot of data, but the policymaker doesn't help the policymaker. You need to really come up with visualization, key performance indicator that measure things. Are things going well or are things going bad? So how can we do that? So the first thing we can do is collect this data on the network and then take one highway in one direction. So what you see at the y-axis here is the highway. So it's the start of the highway until the end of the highway, and you see the time. And each pixel has a color, and the color is the speed. So when you see green, you're fine. So there is nothing. People drive 100 kilometers an hour or higher, so you don't have a problem. But where you see red, then you have traffic jam, so then you don't drive very quickly. So when you look at this heat map, we call it a heat map, you immediately see, I will just walk here, I don't know if I will, so you immediately see we are bleeding here, here, here. These are locations where you have traffic jams, so that's a problem. So you're bleeding, this costs money. So there is a problem here. When you slow down, you don't drive the speed you want. This is the morning peak, when people go in that direction, and this is the evening peak, when the people are coming back from their location. So this is a kind of visualization based on those induction loop detectors. And at the right side, you see the same picture for the same day, but another source is the base. That's floating car data. So the data collected from apps of cars is also collected, and you can see that those two things are almost the same. So this data, these sensors and these sensors produce really the same data. One big difference is these floating car data you see at night. There is a lot of missing data, and that's because people don't drive much their car, so they don't deliver data. So we don't have a lot of data from floating car data, and this is induction loop data. The data I show you, the sensors I show you, they are very reliable, but very expensive in maintenance. So when you want to maintain an induction loop detector, you have to close a lane. This data is very cheap, so there is a trade-off. You can play around with that. Okay, so you can use this raw data, is very important, but you have to extract information from it and then visualize it, so policymaker can see, hey, this highway is not performing very well. I have a lot of congestion. Maybe I have to do something about it. Another thing is when you can combine data. So in this heat map, you can see what we saw already. This is a morning peak. This is a highway. You see here problem, and you see there the evening peak problem. But you see also between the peaks, along the whole highway, you see some speed reduction. People are not driving really with the speed they want to do. Why? There is no peak. It's not the morning peak. It's not the evening peak. Why is this there? So this data doesn't explain it until you add the rain to it. These are the blue dots. There was a heavy, heavy rain that day at that time. So the whole highway was really, everybody was hitting the brake and driving slowly. So this explains a lot of things. So the idea is combining data creates also more context and enrich information. And that's exactly the thing we did here together with EGIS. So we took the storm Eunice, and then storm Eunice happened in the Netherlands, hit the Netherlands on 18th of February 2022. And at TNO, we always look at how can we compare now storm Eunice with a regular day. What is a regular day? So these kind of things, we think about it to generate key performance indicators that help us compare days. So what you see here is different days, and the key performance indicator is the vehicle kilometers. How many vehicle kilometers, how many kilometers were driven each minute by all the vehicles on the network. So you see that the Fridays have the same pattern. So they're just, if each Friday the network absorbs and digests the same thing. So there are really patterns here. But this blue one, this is cyan one, the 18th of February was very different as a pattern. It was different. So that was when the storm hit. So this is, it can give you, when you come up with good indicators, it gives you right away, hey, this is a different pattern. What is going on here? Now, then you can look up on the internet or talk to experts and say, well, that was a storm, yeah, there was rain and things. So you can, here it gives you a measure that this day is an outlier. And we have another indicator that measures the performance of the network, the whole network. You can just take it in one number, and that's the resilience of the network. So usually the network has a performance. We talk a lot about performance, but how do you measure it? We proposed an indicator to measure this thing. And we applied it to this use case with EGIS. And what you see is when you are at 100%, it means the network is doing exactly what it's supposed to do. So everything is going as normal. You see the 4th of March, this a day that was a Friday again, but there was no storm. What you see is the thing is oscillating around 100%, nothing really going on. Storm Eunice, by the way, is completely different. You see that the performance is dropping at a certain moment, so it gives you a lot of information. So how severe was the storm, the depth, and how quickly it recovers to 100%. So these are things for traffic engineers and network managers that are very important. So how resilient is your network for Storm Eunice? And then you can compare it. Is Storm Eunice was heavier than another storm, B, C, and D? So it gives you ways to compare things. So we are very good at coming up with measurements and for policymakers to compare. Is this green or is it red? We don't want red. But visualization is very important. And that's something that EGIS does very, very well. So this was really a joint work to help understand impact and within a context. So we did just, this is a boring visualization, we did just a small, what I usually did before I met Jay is plotting the data and making slices of it, making frames and making a movie. So this is data for Storm Eunice. The data is collected and mapped on the network. You will see water here and you will see congestion there, things becoming red. So this is just the rain falling and corresponding what is the network doing. So where it becomes red there is a problem. So you see here is a big rainfall and you see the impact on the traffic there. So we can quantify exactly how much time is between heavy rain at a certain link and congestion. If I look at another, the day, the reference day, so you can see that there was no rain. You will see nothing. It was a dry day. And at the other side, you see a normal day. There is an evening peak. You will notice that up from 1500 hours, you will see the evening peak very heavily. Yeah. This is the evening peak, 1600 hours, but there is no rain. This is just the business as usual. Usually you have that. And this guy. And one other use case that the Storm Eunice was a typical storm, but there is one thing. It was announced the day before at the news that be careful, this is code red. If you don't have to go to work, please work at home. So people were informed. So it was manageable. Some people stayed at home, so you can see the pattern was completely different and the behavior was different. This one is the worst storm in the Netherlands and its impact was really disastrous. It was a storm that even we didn't know about it. It just came. No one knew, even the meteorological company didn't know about it. And then you can see the impact of it. So I will not say anything, you just watch and see. You don't want to be there. This is very terrible because it's completely blocked. And it stayed there until 8 o'clock in the evening. So it's really a big problem because all the people were at the network in business as usual, and then you get stuck in traffic. Okay. Yeah, so this was the heaviest impact in the history of the Netherlands, really. I will go quickly about digital twinning. Usually when we talk about the digital twin, what people, at least the policymakers, think is we have data and we can visualize data, and that's important. But there is more into it. At least the philosophy of TNO. There are other things that should be considered. The analytics and the visual. These three things are very, very important for a digital twin to be successful and to be serving as a decision support system. It is more elaborate than you think. I am personally more active in those two things, somehow a little active there, but mainly in those two things. I design key performance indicators that really the policymaker can look at and see either my policy is doing well or it's not doing well, and the data is very important. So, I will end with the key main takeaway. So, if you want to build a digital twin in a way that it is transparent and explainable, these things are very important. So you need data, and data is really, really important. If you don't have data, you just stop there, right there. Visualization is as important as data. You can have data, but you can't really extract the information and show it in an intuitive way. It won't work. It won't help the policymaker. And you need to tackle the problem from different domains, not just one. You have to couple domains. You have to couple the energy to mobility, to well-being. All are interconnected. So you have to break the silos. And once you have the digital twin and you're satisfied, it is an ongoing process. So you don't stop there because data change, network change, everything. So there is maintenance. You need to maintain it in order to rely on it in a reliable way. And explainability for a policymaker is very important. If the policymaker cannot explain to the population why these decisions were made, the policymaker won't use it. So that's very important. Okay, I think I will stop here. EGIS did with the data, so it is really an interplay between visualization and analytics. So that's. Thank you very much.
TNO의 발표를 잘 들으셨으리라 생각합니다. TNO가 수행한 시뮬레이션은 그 네덜란드 교통국의 요청으로 강우 발생 시 교통 네트워크의 취약 지점을 식별하기 위해 수행된 프로젝트입니다. 즉, 교통이 악화됐을 때 우리는 정말 그 원인을 이해하고 있는가? 라는 질문에서 출발했습니다. 여기까지가 TNO의 역할이고 이 지점에서 EGIS의 역할이 시작됩니다. 우리는 TNO의 모델이나 산출 결과를 변경하지 않았습니다. 그 결과를 그대로 활용했습니다. 대신에 그 데이터를 의사결정자가 어떻게 이해할 수 있는가의 관점에서 다시 구조화했습니다. 2차원은 무엇이 일어났는가를 우리에게 보여줍니다. 그러나 3차원은 어디서, 왜, 얼마나 위험한가를 직관적으로 드러냅니다. 데이터의 3차원화는 단순한 시각적 개선이 아닙니다. 의사결정 속도를 높이기 위한 구조적인 선택입니다. 우리는 TNO의 모델을 바꾸지 않았고 단지 EGIS 디지털 어스 플랫폼 내에서 데이터를 바라보는 관점을 바꾸었습니다. 네덜란드 기상과 교통 데이터를 기반으로 TNO에서 시뮬레이션을 수행하였고 그 산출된 결과를 기반으로 EGIS에서 공간 매핑 및 고도 정합을 통해서 3차원 디지털 어스 실행 환경을 구현하였습니다. 이를 통해 정책 및 운영 의사결정 지원 플랫폼의 토대를 마련하고자 하였습니다. 이렇듯 바뀐 것은 데이터가 아니라 데이터를 사용하는 방식, 즉 데이터를 바라보는 관점입니다. 의사결정 지원 플랫폼의 전제는 공간에 대한 신뢰성입니다. 우리는 공간 신뢰성을 확보하기 위해 TNO 측에서 순차적으로 제공받은 데이터를 활용하여 좌표 정합, 고도 정합 및 방향성 구현 등을 단계적으로 수행하였습니다. 시점이 바뀌면 질문이 달라집니다. 질문이 달라지면 의사결정, 즉 정책도 달라집니다. 우리는 세 가지 시점으로 나누어 데이터를 구현하였습니다. 원거리 시점을 통해서 국가 및 전체 네트워크 단위의 교통 패턴을 확인하고자 하였으며 중거리 관점을 통해서 특정 정체 구간 및 사고의 영향 범위를 파악하고자 하였습니다. 그리고 근거리 시점을 통해서 개별 차량의 방향성, 속도, 그리고 입체 교차 구조를 상세히 확인할 수 있도록 하였습니다. 이렇듯 플랫폼은 질문의 수준과 단계에 맞추어 그에 맞는 정보의 밀도를 제공합니다. 지금 보시는 화면은 이번 POC의 최종 성과를 실제 도메인 기반 플랫폼에서 구현한 모습을 보여줍니다. 실제 여러 가지 비교를 할 수 있도록 도로별로 데이터 테이블을 마련하였고, 그리고 강우와 실제 교통 속도와의 상관관계를 확인하기 위해서 동시에 도표화를 할 수 있도록 하였으며, 또는 여러 가지 도로별 현재의 속도와 평균 속도, 현재의 강우량과 평균 강우량을 확인할 수 있게끔 통계 도표도 생성하였습니다. 또한 네덜란드 왕립기상청에서 제공한 강우 라이다 자료를 실제 위에 도식화를 해서 실제 구름과 강우의 변화가 어떻게 이루어지는지도 확인할 수 있게끔 하였습니다. 지금 화면에 보시는 빨간색이 정체 구간을 표시하는 것이고, 직관적인 시각화를 위해서 속도가 더딘 구역을 빨갛게 크게 가시화를 하였습니다. 그 외에 파란색은 정상적인 속도를 나타낼 수 있는 것입니다. 또한 지금 속도별로 범례 필터링을 통해서 우리가 원하는 부분의 데이터만 확인할 수 있게끔 했습니다. 지금은 이제 원활한 구역의 범례를 필터링을 함으로써 지금 정체 구역만 확대해서 볼 수 있도록 하였습니다. 만약 강우량이 시간당 20mm 이상일 때 속도의 변동성이 35% 증가한다면 담당자는 해당 도로의 사전 통제나 우회 도로 안내가 필요하다는 판단을 내릴 수 있습니다. 이 순간 데이터는 단순한 정보가 아니라 행동으로 전환됩니다. 플랫폼은 단순한 보고 도구가 아니라 통제 도구가 됩니다. 그리고 이 판단은 직관에 의존하지 않습니다. 정량적 비교를 기반으로 합니다. 폭풍 유니스가 강타한 날은 금요일이었습니다. 타우픽 박사님께서 보여주신 것처럼 네덜란드의 교통 패턴은 월요일과 금요일이 주말과 연결되어 그 패턴이 유사하고, 화요일과 목요일은 일상적인 평일의 패턴이며 수요일은 학교가 일찍 마치는 날이므로 또 다른 교통 패턴을 보여준다고 합니다. 이에 우리는 비가 거의 내리지 않는 일반적인 금요일의 패턴과 폭풍 유니스가 강타한 날의 패턴을 비교하였습니다. 하단부의 같은 시간대의 좌측에 지금 현재 선택되어 있던 폭풍 시점과 우측의 일상적인 시점을 같은 시간대에 비교함으로써 그 차이를 확인할 수 있게끔 하였습니다. 일상적인 날에는 오후 4시가 넘어서 퇴근 시간과 맞물려 교통 정체가 발생하는 등 일정한 패턴을 확인할 수 있습니다. 그러나 보시는 것과 같이 코드 레드 상황에서는 리스크가 네트워크 단위로 확산됩니다. 차이는 데이터의 존재 여부가 아니라 변동성이 어떤 패턴과 체계를 가지고 나타나는가, 즉 변동성의 구조입니다. 우리는 그 변동성을 직관적으로 보이게 만들었습니다. 단순한 데이터의 평균이 아닌 리스크가 어떻게 확산되는가, 그 사실에 집중하였습니다. 이렇듯 성공적으로 수행한 근본 POC는 향후 인지 및 예측, 그리고 자동 대응의 3단계로 확장될 예정입니다. AI 에이전트가 스스로 기상 데이터를 수집 및 분석하고 교통 네트워크 전체 리스크를 분석합니다. 이를 통해 운영자의 개입을 최소화하고 의사결정을 더욱 빠르고 일관되게 할 수 있습니다. 이제 질문은 더 이상 보여줄 수 있는가에 국한된 것이 아니라 스스로 대응할 수 있는가입니다. 이를 위해 TNO와 EGIS는 모빌리티 에이전트 오토메이션을 목표로 다방면으로 협업을 이어나갈 계획입니다. 데이터는 이미 존재합니다. 이제 필요한 것은 그것을 의사결정 구조로 만드는 플랫폼입니다. 그리고 이것이 우리가 TNO와 함께 시작한 첫 단계입니다. EGIS는 단순히 데이터를 가시화하는 도구를 만드는 것이 아니라 결정을 설계하는 인프라를 만들고 있습니다. 감사합니다.
네, 감사합니다. 두 분의 발표 잘 들었습니다.